Assalamualaikum warahmatullahi wabarakatuh. A very good day. For chapter number 5, part number 5, we will start our discussion with stage performance losses. Energy losses flow diagram for a compressor stage. So for this slide, we want to know different type of energy losses involved with compressor stage, and also we want to know why the actual energy that we need to supply to the compressor is greater than the work for the ideal case. So the figure shows the cross section of the compressor. So we have inlet point, guide vane, bearing, shaft bearing, stator blade, rotor disc, shaft, compressor shaft, stator, and also exit point of the compressor. So if you know, uh, we already learned that for the work that we need to supply to the compressor, for ideal case where we ignore all the losses, so we will consider the energy or work as the isentropic work delta W minimum, where this value represent the ideal work to obtain the stage rise in the compressor, delta P, where delta P equal to pressure at the exit minus pressure at the inlet. Let's say we need to provide, for example, as example, let's say the isentropic work of the compression process. Let's say we need to provide to the compressor around 82 kilojoule. Okay, due to the losses. So the first losses that we refer to is the stator aerodynamic losses. If you look at the figure shows the what I call the stator blade arrangement, where the stator blade normally attached to the casing, and there are three types of losses involved for the aerodynamic losses for the stator. First we have the profile loss, secondary loss, and also the annulus loss. And we assume that the value of stator aerodynamic losses is around 7 kilojoule. Okay, due to the losses, energy at the stator entry that represented by W entry or entry work, we need to provide more energy in order to maintain the value of isentropic work uh, value at 82 kilojoule. So energy at the stator entry after we include the value of stator aerodynamic losses, so we will have entry work equal to 89 kilojoule. Okay, in the compressor stage that involve rotor movement and also the what I call the stator what I call effect. So we will have another type of losses that we call rotor aerodynamic losses. That the losses that caused by the rotational movement of the rotor of the compressor. So the figure shows the arrangement or the rotor blade features in the compressor, where the rotor blade is attached on the rotor hub, and there are four types of losses involved due to the aerodynamic losses for the rotor. So we have profile loss, annulus loss, secondary loss, and the other one is the tip leakage losses. And for example, let's say the value of rotor aerodynamic losses is around 9 kilojoule. So now the stage work delta W, which is represent the actual stage work, so we need to provide more energy due to the losses after we consider rotor aerodynamic losses and also stator aerodynamic losses. So we need to provide actual stage work energy equal to 98 kilojoule, which is in comparison is more than the isentropic work. And further, due to the rotational movement of the shaft, compressor shaft, we also have different type of losses that we call shaft losses. There are two types of losses due to shaft rotational movement of the compressor. So we have this friction loss and also bearing loss. So let's say the amount of shaft losses in terms of energy losses is around 2 kilojoule. So uh, the overall energy that we need to supply to the compressor actually come from the prime mover. So energy from the prime mover, or we call shaft work, W shaft, that we need to supply to the compressor after we consider a various type of losses is around 100 kilojoule. So that's why if you compare in terms of value uh, between the actual uh, amount of energy that we need to supply to the compressor compared to the ideal energy that we need to supply to the compressor is different, where energy, the actual energy or the actual work will be greater compared to the isentropic work or ideal work. These are the reason why we need to supply more I call work to the compressor for the actual process. So for this example, in overall we need to have additional energy around 18 kilojoule. Okay, in order to maintain the isentropic work at 82 kilojoule. Okay, so if we need to calculate the overall efficiency mu 0 or mu naught, so mu naught overall efficiency equal to delta W minimum uh, that refer to the isentropic work divided by W shaft, the energy from the prime mover. So we have 82 divided by 100. So the overall efficiency of the compression process for this example is 82%. And also we can calculate the stage efficiency, where stage efficiency mu s also equal to total efficiency, where stage efficiency equal to delta W minimum isentropic work divided by delta W actual stage work. So we have 82 divided by 19.8. So we'll get stage efficiency equal to 84%. So now from this slide, we already learned that there are various type of losses involved in the actual process of the compressor, and also we already know that why the value of what I call for in terms of energy supplied in the actual process is greater than energy supplied for the ideal compression process in the compressor. And also we also know the difference between overall efficiency and also stage efficiency in this example. Okay, so that's what I call the discussion about the energy losses in the compressor. Estimation of compressor stage efficiency mu s. So for normal stage condition, the stage efficiency mu s actually is similar to total efficiency mu tt. So mu s more or less equal to mu tt. So we can determine the stage efficiency for the compressor by using this formula, where mu tt equal to 1 minus delta p naught for the rotor plus delta p naught for the stator divided by rho h03 minus h01. For the value of delta P naught for both rotor and stator, we can determine by using cascade data that obtained by Howell 1942. So you already learned this graph as shown in the slide. So from this graph, we can determine delta P naught for the stator and also delta P naught for the rotor, and we can substitute into the equation for total efficiency. However, this data of Howell 1942 only consider the blade profile loss due to the profile drag coefficient CDP. Okay, so from Howell 1942 we only obtain delta P naught or total pressure loss based on profile loss. Okay. However, for realistic total pressure loss values, we need to add different type of losses such as secondary flow and also annulus losses in our calculation. Okay, so based on the total pressure loss coefficient zeta and also profile drag coefficient CDP equation in chapter number 2 that we have learned, we will obtain this formula that represented by equation number 1. Delta P naught equal to rho Cx square multiplied by CD drag coefficient divided by 2 multiplied by S over L cos cubic alpha M. Okay, the value of CD. So in order to obtain delta P naught based on the secondary losses, so the value for CD in equation number 1, we need to substitute with the value of CD drag coefficient for the secondary drag coefficient that represented by CDS. And CDS we can calculate by using this formula. CDS equal to 0.018 CL square, where CL stand for lift coefficient. So we will get delta P naught total pressure loss due to the secondary losses. So if you want to obtain delta P naught due to annulus losses, so we need to include CDA drag coefficient due to annulus losses, where CDA formula equal to 0.02 multiplied by S over H. S stand for spacing distance, H stand for blade height. So CDA value we need to substitute into equation number 1. So we will get total pressure loss delta P naught based on the annulus loss delta P naught A. Okay, so in order to obtain more accurate total efficiency, so we need to combine different type of I call total pressure loss due to different type of losses. So we combine all the total pressure loss delta P naught due to profile losses, annulus losses, and secondary losses, and then we substitute this total what I call total pressure losses into the equation for total efficiency. So we will get more accurate total efficiency based on various type of losses in the compressor. Okay, so we can calculate what I call both for the delta P naught rotor and also delta P naught stator after we consider different type of losses. Okay. Okay, for the term of enthalpy difference or actual work, H03 minus H01 in total efficiency equation. So we know that H03 minus H01 based on Euler equation equal to U Cy2 minus Cy1. So this value we can determine by using velocity diagram. However, this calculation actually based on two-dimensional analysis where we assume that constant value of axial velocity Cx throughout the compression process. However, different for 3D analysis. Normally, we need to consider 3D analysis for multi-stages compressor, where we need to consider secondary flow and also annulus flow effect, because these two type of effect will cause non-uniform axial velocity that we need to consider. Okay, so this figure shows the cross section, the simplified cross section of the compressor, multi-stages compressor. So we have casing, hub, and also annulus height. And from this figure, we want to show the axial velocity profile for both cases, for uniform axial velocity and also non-uniform axial velocity. So we have airflow direction into the compressor. We have stage number 1. For the uniform axial velocity, what I call the vertical red color line represent the uniform axial velocity for stage number 1, stage number 2, and also stage number 3. However, if we consider 3D analysis, where we consider secondary flow and also annulus flow effect, so we will get the what I call the axial velocity profile that represent by blue color curve. So this blue color curve represent non-uniform axial velocity profile for 3D analysis. Thus, in order to obtain the actual work H03 minus H01 for the 3D analysis, for 3D three-dimensional case, so we need to add what I call one parameter that we call lambda multiply with u cy2 minus cy1 that represent by equation number 2, and lambda is represent the work done factor, and normally we need to use this lambda value for multi-stages compressor. And normally for multi-stages compressor, typical multi-stages compressor, the value of lambda is around 0.86. Okay, in terms of work done factor for different I call different numbers of stages for the compressor, we can determine by using this graph. So this graph shows the mean work done factor lambda versus number of stages in the compressor. So from this graph, if we know the number of stages of the compressor, we can determine the value of lambda and then include the value of lambda or substitute the value of lambda into equation number 2. So we will get the actual work H03 minus H01 for 3D analysis of the compression process. So if you refer to the value of work done factor equal to 0.86, we can determine that the value actually suitable for the number of stages in the compressor, which is equal to 10 stages. So from this graph, we can determine, if you have lambda value, we can determine the number of stages involved. Or if we want to determine lambda, we need to know the value of stages in the compressor. Then we can determine the value of mean work done factor before we substitute the value into equation number 2 to determine the actual stage work before we substitute into total efficiency equation. Okay, so by considering these two factors based on the total pressure losses and also actual stage work for the more realistic condition, so we will get more accurate total efficiency for the compressor stage. Axial flow compressor, surge and stall. So there are two phenomena that cause energy losses in the compressor that we call surging phenomena and also stalling phenomena. Unstable flow in the compressor due to surge phenomena. Surging actually refers to the flow through the entire compressor is reversed intermittently, where the stopping and also the starting uh, surging process repeatedly occur in this phenomena. So due to this phenomena will cause the complete breakdown of the normal steady flow and will affect the whole machine. So this phenomena will affect the whole compressor. So in order to explain the surging phenomena, we need to refer to the what I call the compressor maps. So the compressor map will shows the relationship in terms of pressurized delta P versus flow rate m dot. Okay, so we have in this graph or in this compressor map we have numbers of different curve for the call the rotational speed. So we have numbers of constant speed line n1, n2, n3, and also n4, where n4 greater than n3, n3 greater than n2, n2 greater than n1. So if we look at the constant specific line, if we reduce the flow rate m dot value, the pressure rise will be increased as shown in the graph. Okay, so at certain point we will have point S that refer as the surge point, and after this point the pressure rise will decrease due to the surging phenomena. So any reduction of flow rate will not increase the pressure rise. So after this point, the decrease of flow rate will cause the decrease of pressure rise in the compressor, as shown by point D and also point E. So the dashed blue color line or blue color curve represent the surge cycle, and point D refer as the last valve condition. Okay, so for the surging phenomena, we already learned in previous chapter, where this figure shows the arrangement of the compressor blade. So we have pressure at the inlet P1, pressure at the outlet P2. We have blade speed direction U. So for the compressor, when the what we call the rotor of the compressor rotate, the fluid will enter the compressor and the pressure rise at the outlet of the compressor will increase. So at a certain point where the pressure too high, so the reverse flow will occur, surging surging will occur. At this point, surging will occur. And when reverse flow occur at the outlet of the compressor, the pressure P2 will reduce again, and because the compressor is set at a specific operation condition, so the compressor will suck more air in order to maintain the pressure rise or pressure ratio for the compressor. So this process will keep repeating if we not change the call the parameter of the operation condition. So this is the basic of the surging, where the formation in the process call in the compressor will have the reverse flow occur during the compression process. Okay, so in the compressor map we have numbers of for each constant speed line we will have point S that refer as the if you combine all the point, we will have surge line, which refer the limit, what I call the minimum value for flow rate for each constant speed line. Okay, so this surging phenomena will what I call will keep repeating if we didn't change the condition of the compressor. Okay, and this will cause excessive vibration that cause further the mechanical failure. So the indication of surging phenomena are, so we'll have pulsating noise level will increase, axial shaft position change of the compressor, axial shaft uh, for the compressor position will change, discharge temperature, excursion will increase, so we will have a drastic temperature increase, differential pressure fluctuation, lateral, and the last one is the lateral vibration amplitude also will increase. So in the compressor map, we also have the second limit line that refer as the choke line, where for this second limit, for choking process or choking phenomena, the flow in the compressor reach Mach number equal to 1 at the blade inlet, where Mach number actually equal to C fluid velocity divided by A sound speed, also equal to C divided by square root gamma RT. So at this point, no more flow can pass through the compressor, although we increase the value of flow rate m dot. So if you if we use what I call higher number of stages for the compressor, we can increase pressure ratio value, and also we can increase the operational margin between surge point and also the choke point. Okay, we can increase the operational margin between surge and choke as shown in the figure. So we have more option. Okay, the second phenomena that cause unstable flow in the compressor is referred to the stalling phenomena. So stalling phenomena and also surging phenomena is quite similar. You can say that stalling phenomena is the subset of the surging phenomena. Okay, so for stalling phenomena is referred to the separation of flow from the blade surface, as we have learned in previous chapter. So we already, if you refer to the figures of CLCD versus angle of attack, we can see there are two separate regions. So we have attached flow region and also separated flow region. So the stalling phenomena will occur within the separated flow region after the critical point of angle of attack. So the stalling phenomena refer as a local phenomenon, and this stalling phenomena will cause delivery pressure at the outlet of the compressor will reduce due to reverse flow or surging, and this also will cause stage efficiency of the compressor will reduce due to the high losses when the separation flow occur from the blade surface of the compressor. Okay, so this stalling phenomena have close relation to the rotating stall. Actually, in the actual process, in the actual compressor, the stalling phenomena will occur in in the form of rotating stall, where the stall phenomena propagate from blade to blade. Okay, for example, in order to explain the rotating stall, we need to look at this figure, where the figure shows the arrangement of the rotor blade of the compressor. So we have 1, 2, 3, 4. Okay, so the upper side of the blade we refer as the suction side, and the lower surface we refer as the pressure side. So we have the direction of the blade speed of the rotor, compressor rotor. Okay, we have trailing, sorry, we have what I call H line, and we have the direction of fluid at the inlet of the compressor. Okay, let's say this is in the angle of the what I call velocity at the inlet will cause this separation. and this incident angle already enter the critical angle of attack. And on the surface at the suction side of the blade will have separated flow occur. And this phenomena at this local point of the blade we refer as the stalling phenomena. However, in actual condition, throughout the what I call the blade passage, so we will have flow deflection. So the angle is not in term of the angle of the incident angle for the blade is not constant. So we will have at the same passage of the blade we will have what I call angle deflection. So we will have different incident angle. Okay. So um, what I call to the section the blade location to the what I call to the left side of this figure, the what I call the incident angle value will increase. So for blade number 3 and blade number 4, so we'll have a propagating stall cell on the surface of the blade. Okay, due to the increase of the incident angle. So this incident angle will be higher than the critical angle of attack. Okay. However, for blade number 2, blade number 1, the condition is different where the incident angle reduce and no separation flow or minimum separation flow occur on the surface on the suction side of the blade number 1 and also blade number 2. So no stalling phenomena occur on the blade number 2 and also on the blade number 1. So for the what I call for the right side blade, so no stalling phenomena occur on the surface due to the decreasing incident angle value during the I call compression process. So this phenomena we call rotating stall. So the stall phenomena on individual blade will propagate from blade to blade. So now due to the rotating stall phenomena, the blade are subjected to force vibration. So the vibration on the individual blade will occur. Okay, to test your understanding for part number 5, chapter number 5, please answer the question below. First question, what is the difference between overall efficiency and stage efficiency? Question number 2, what is the difference between total to total efficiency and stage efficiency? Question number 3, what is the difference between surging and stalling? So you have to answer the question by clicking the link provided in my blog. Remember that you need to know the password in order to open the link. The password was given throughout the video related to this topic. The clue is also given in the link. Okay, so that's all for chapter number 5, part number 5. So end of chapter number 5. So now you need to study for your final exam and try to search in YouTube the related video for each chapter. So I try to provide the video for different chapters in my blog. So that's all. Assalamualaikum.